Hi and welcome to another video about Hopper on the Raspberry Pi Pico. Hopper is a modern semicolon and curly brace language similar to Java and C#, but designed to run on small platforms. It runs on the 6502, for example. I've improved the performance of Hopper since I first uploaded on the Pi Pico, since I first uploaded a few videos. It's quite dramatic. So let me just illustrate quickly. So I use a couple of benchmarks. The one that I've been using on the 6502, so I know how fast it is. So this is running a lot faster than the 6502. When I first ran that on the Pi Pico, it took about 21 seconds. Now it takes 3.5 seconds. The other benchmark is the Fibonacci 24 benchmark. And I chose this because I found some stuff online about someone else benchmarking it on Python using MicroPython and the various different accelerators. And about last time I posted videos a couple of days ago, it was running in about 8 seconds, so about 4 or 5 times slower than Python. It now runs marginally faster than sort of not an accelerated Python, the sort of default MicroPython. So it's running in under 2 seconds. So I'm pretty happy with that. Yeah, there's not a lot's going to happen on the device today. All you see it is in the console. So it's a serial connection to the Pi Pico. How did I do this? That's what I did is the original, the port is still a pretty naive port. I've written the runtime in Hopper and then cross-compiled it with a code generator that takes Hopper virtual machine instructions and converts them to C. So it's not a very quick way of. It won't be very, very fast ever. I'll have to hand code a runtime for the Raspberry Pi Pico if I ever want it to be super fast. In the meantime, this is pretty portable. So what I did is the original version of it had a big switch statement for each of the opcodes in the virtual machine. I switched to using Hopper's delegates, which are function pointers, made a big table of function pointers and moved every opcode into its own little function because they were all in a big switch statement. So I'll just scroll down a little bit more. So each one, like add has a little function, subtract has a little function, multiply has a little function, rather than having a big switch statement. So I think if we look at the way the system calls are done, you can see what the switch statement version looks like. Execute sys. Yeah. So this is how the system calls are done. It's a big switch statement on an integer to switch between each of the system calls. So you have a switch statement that goes on for 2,000 lines. So this is how the opcodes were working as well, with a big switch statement. And even though the switch statement does a clever lookup with a table, it's still way less efficient than just using a jump table and using function pointers. And then the code that does the actual jumping is down here. So when it's not running in the debugger, I run this way. So it'll just continue so it'll pull out an opcode out of the memory. Then it'll look in the jump table for the address, which is actually a Hopper delegate. And then it'll just execute that delegate. And then if the result of that says carry on, it'll just continue around back up to here and do a very quick loop. The result saying not carry on is if there was an error, division by 0, a range error, or if the program exited. Those are basically the two most common exit conditions. And then when it's running on the microcontroller, I optimize this even further by resolving the delegate to an actual address. So instead of having to look up methods in a table, I'm just jumping straight to them when I'm in the C. Anyway, it's a good illustration of function pointers and delegates in Hopper. So when it's running in Hopper on Windows, it's using these delegates, and it's still pretty fast. Anyway, I'm very happy with this. improvement. So let's just end on a Mandelbrot. Anyway, I look forward to your feedback. Thanks for watching.